Okay, Timothy, go ahead.
Hi, thank you. I'm Tim Carleton. I'm a research scientist at Arizona State University, and I want to talk to you a little bit today about our WFS program to model the large-scale backgrounds in Roman data. And this is a program I've been lucky to work with a relatively small team of people that are shown here, and I'm really excited to kind of show some of the modeling that we can do and some of the benefits that this program can have for wide field science. All right, so to just kind of motivate what we're doing here a little bit, first I'll show this image. This is a really nice image of real data. This is Euclid's, one of Euclid's ERO images of the Virgo or the Fornax cluster. Hopefully we'll have a really nice real image of Roman data to start some talks off in the future. And obviously this is really nice. You get to see lots of really cool galaxies. But if you kind of stretch the image a little bit, you can just kind of stretch it with PowerPoint, you can kind of see a little bit of mess. And this isn't anything to do with the calibration or the instrument or anything. This is just stuff that's in between us or wherever you're at L2 and the distant galaxies that we're interested in studying. And so we have some bright stars you can kind of see scattered throughout the image. And in particular in this field, there's some nasty galactic cirrus that's kind of poking through in your image. And this is something we want to, this is going to be in Roman images as well, and we want to kind of understand what's going on and see what we can do with that. And so to kind of motivate our approach to looking at this type of data, I want to distinguish between what I'll call background estimation with empirical data and background modeling. And just to kind of illustrate it, I picked out a particularly nasty region in that ERO image where you can see some really nasty galactic cirrus and some bright stars in there as well. And so I'm considering two different approaches here. One is empirical estimation of the background using just the data we have available, as well as physically motivated background model that uses both ancillary data of stuff that we know is going on and the image data that we have. And so you can kind of imagine two approaches here, where if you just use the image data that's readily available, then you kind of get this middle image. And if you use a more physically motivated model for the background, you're able to get this cleaner and more kind of foreground-free image on the right. And so the differences here, the empirical estimation is really primarily sensitive to smooth variation across the image, whereas a physically motivated model can be sensitive both to smooth and more sharp variation within the image. So like diffraction spikes, galactic cirrus, we know has a particular shape. We can model those out and get a smoother overall image. Another nice thing about kind of doing this more physically motivated modeling is that you're able to kind of separate out the components of the background in your image. Rather than just saying this is something that's not a galaxy, you're able to identify diffuse galactic cirrus, you're able to identify zodiacal light, that's your foreground, and you're able to enable kind of some wide field science that you can do with those separated out background components. That being said, this approach of empirical estimation is much more efficient and usually good enough. And so I'm not saying that we need to completely redo the pipeline to get our science, but I would say that doing some physically motivated modeling of the backgrounds that we see can enable a lot of really interesting science. And so just to kind of illustrate some of the specific scientific benefits that we could have from this modeling, first of all, if you're interested in large or diffuse galaxies, you're able to get much more accurate photometry if you're able to have a better background model on large scales, and so you can have improved photometry. You can also be more sensitive to large, low surface brightness and ultra-diffuse galaxies. These are galaxies that I'm particularly interested in, and by having this better background on large scales, you're able to identify those a little bit better. But then also there's a lot of science, like I said, in studying the overall backgrounds themselves. For example, the structure of the zodiacal cloud or in our solar system, the spectral energy distribution of galactic cirrus, and the kind of clustering of extragalactic background light are just a few examples that I've shown here. And so this all looks really cool. How are we going to do this? And so with any given WFI image, we plan on our pipeline will break that image up into the background of that image up into 4 distinct components. First of all, for any extragalactic field, the primary background will be zodiacal light. And so we're using the latest and greatest zodiacal light model from Rosalie O'Brien based on the 30-year Hubble archive. And so you have that ZODI model. I'll say for Roman, we expect there to be places where the background, the zodiacal light background, we expect that to vary on the order of 1% or so. And so this is something that we'll have to kind of model throughout the image. We'll also have a model for bright stars, the wings of the PSF. We have a kind of in development custom wide angle PSF model. I'd be happy to answer any questions about. We also have a model for galactic cirrus. This is based on King Lu's model that he developed for the Dragonfly telescope that correlates Planck emission with kind of the streamy structure in an image to identify kind of where you expect diffuse galactic cirrus to be. And we also have thermal emission from the telescope that we expect to be non-negligible, especially in the K-band. And we also incorporate the effect that this may vary over the course of an orbit, which is something we've seen in HST data. And so once you put all those components together, you can study any of them individually, or you can subtract them all from your image and get a really nice, clean image for extragalactic science. And so here is SUPERBACK. We are able to, we will release code to simulate some more complex backgrounds than you would kind of imagine and is kind of currently available. And we will also have code that will model the backgrounds that you see into these individual components and allow you to kind of study them individually. So with that, thank you. I'll take any questions.
Could you go back to the earlier slide where you showed the comparison between SUPERBACK and the traditional subtraction method? It's one of the early slides. Not quite. Yeah, there it is. Okay, so I stared at that the whole time it was up there, and clearly SUPERBACK, you know, the one on the right, it is nicer generally. The thing that confused me is I thought I spotted a few things in the middle image that looked like real objects, which I couldn't really find them after SUPERBACK got through cleaning it up. I wonder if one or two real, I don't know, sources of light got taken out that shouldn't have.
Okay, so I'll say the main thing that's going on in this image subtraction is with the galactic cirrus that you're seeing, and the way that that works is you have a Planck map, and you look for extended and elongated structure that's correlated with the Planck emission that you expect in that region. And so if you have a large structure that looks like cirrus, then it's possible it could be subtracted off and interpreted as cirrus. Okay. Yeah, we can talk later.
Okay, other questions?
I was just wondering if you can talk a little bit more about your PSF model and like what goes in there, what kind of optical instabilities or errors are you sensitive to or care about the most to develop it at high fidelity?
I went one too far. So thank you. So this is the PSF model that we're working on. And I'll say I'm interested in the wide angles of bright stars. And so this I'm modeling just as this, basically you get the diffraction spikes as some sine x over x of the bars of the struts that you expect to see. And so I've kind of tested this approach with JWST data, and it seems to work out pretty well. But the idea is you kind of, by focusing on the wide angles of the PSF, you're able to, you're less sensitive to kind of errors in the specific modeling of the mirror, et cetera. But yeah, I'd be happy to chat more.
Okay, other questions? If it would be all right, I'll go ahead and ask one myself. So I'm also interested in the PSF models that you have. Have you, so I have two questions, if it would be okay, and we have a little bit of time. Would it be all right if you talked about, have you used TVAC data to specifically look and test this out? Because you have simulation to simulation right now, so.
Yeah, that is something that is on my to-do list. I've gone to the website, I've downloaded some data, but I haven't looked at it more specifically.
And in full disclosure, I actually have been to your website, so because I'm very curious about this. Can you talk to me a little bit about the temporal resolution? Because you're looking at Zodi. Can you speak to that just a little bit, please?
Yeah, I mean, so the like you said, Zodi is going to be an important component of the model, and the zodiacal model that we have is, so this is based on, this is a physical model of the dust within the solar system, and we have the scattering physics optimized to kind of what we've seen with HST, and so it is absolutely sensitive to any kind of changes over the course of a couple days or so. You'll be able to kind of account for that.
So I'll be able to pull that accordingly.
Yeah, you can give day of year is it's going to be one of the things where you can put that into the model, and it'll give you the expected zodiacal background on that day of the year in that position.
Okay, we have time for one more question. Yeah, Tom?
Yeah, I was just curious for an update on where it stands on being ready for the exact status right now, and from a personal point of view, how ready is it going to be for use during commissioning?
Oh, it's a great question. So this is, right now, I will say it's not ready yet, but I expect that we'll have something available by the time commissioning comes on, and we'll be able to kind of refine it as commissioning data comes in.
Great, thank you. Wow, that gives me an idea for an opportunity car. Anyway, thank you very much. I really appreciate it. Let's go ahead and thank our speaker again.